Hello everyone. Today I will be presenting about HornSAT and answer the following questions. What constitutes horn clauses? How to check satisfiability of horn clauses? And then I will switch to two important classes of SAT solvers, namely linear SAT solvers and cubic SAT solvers. We will then learn about the algorithms behind these SAT solvers and more about their runtime complexity. To start with, let us keep in mind the broader objective of logic in computer science. The aim of logic in computer science is to develop languages to model the situations we encounter as computer science professionals in such a way that we can reason about them formally. One important instance of encounter mentioned above is that of satisfiability. Many important classes of problems can be boiled down to Boolean set problems. Although 3-set problem is NP hard, but it's worthwhile to investigate some SAT solvers that can provide solutions to some particular classes of SAT problems. So let us start with the first question. What is HornSAT? A horn clause is a clause with at most one positive literal, called the head of the clause, and any number of negative literals forming the body of the clause. A horn formula is a proposition formula formed by conjunction of horn clauses. We know that formulas in conjunctive normal form have an easy syntactic check for validity, but its test for satisfiability is very hard in general. But horn formulas have much more efficient ways of deciding their satisfiability. We shortly define them and give an algorithm for checking their satisfiability. The name Horn is derived from the logician Alfred Horn's last name, who came up with these set of formulas. Recall that the logical constants bottom and top denote an unsatisfiable formula and a tautology respectively. A Horn formula is a formula phi of propositional logic if it can be generated as an instance of H in this grammar defined in the slide. P consists of top, bottom, and atomic proposition denoted by small p. A consists of conjunctions of P. We call each instance of C a horn clause. A horn clause is an implication whose assumption A is a conjunction of propositions of type P and whose conclusion is also of type P. Examples of horn formulas are provided in the slide. We can see in the first example that the formula is a conjunction of three clauses. Each clause is of the type defined above. The first clause is conjunction of P, Q and S implying P, where P, Q and S are atomic propositions. Similarly, the second and the third clause. HornSAT algorithm consists of marking the atomic propositions in a certain manner as explained. To start with, mark top if it occurs in the Horn formula. Apply step 2 of the formula in an iterative manner. If there is a conjunction of marked atomic propositions as an assumption of an implication in a Horn clause, then mark the atomic proposition which is the conclusion of that implication. So this is what step 2 is. Repeat step 2 until it cannot be performed further. If at any point bottom is marked, then this means that the Horn formula is unsatisfiable. If not, then the Horn formula is satisfiable. The previously explained algorithm can be represented in a form of a simple pseudocode. Step 1. Mark all occurrences of top in phi. Step 2. While there is a conjunction of p's in phi such that all p's are marked, then mark the conclusion of the implication as well. Step 3. If bottom is marked, formula is unsatisfiable, else the formula is satisfiable. Some concluding remarks. The runtime of HornSAT algorithm is linear in the number of atomic propositions. This idea of marking atomic propositions will be the underlying idea in linear and cubic SAT solvers. Now, we will move on to SAT solvers. As mentioned before, the SAT solvers being presented here are based on the marking technique presented in the HornSAT. The marking algorithm for Horn formulas computes marks as constraints on all valuations that can make a formula true. All marked subformulas evaluate to their mark values for all valuations in which phi evaluates to true. A SAT solver is a tool that takes as input a CNF formula and outputs either a satisfying Boolean assignment to the variables used in the CNF formula if the formula is consistent, or unsat if it is not. There are two types of SAT solvers that will be discussed here. The first one will be linear SAT solver and the other one will be cubic SAT solver. The first step for the linear SAT solver is to transform the given formula such that the parse tree of the transformed formula consists of conjunction and negation nodes. The inductively defined translations on the bottom left of the slide shows the procedure to transform the given formula. T of phi is the transformed formula. Phi is satisfiable if and only if T of phi is satisfiable, and the set of valuations for which phi is true equals the set of valuations for which T of phi is true. The latter ensures that the diagnostics of a SAT solver applied to the transformed formula is meaningful for the original formula. Let us try to understand this with an example. The transformed formula for the given formula is shown in the slide. Note that the transformed formula consists of only conjunction and negation operation. Now, the directed acyclic graph of the transformed formula will be studied, which is presented in the next slide. Before we move on to study the parse tree of the example presented in the previous slide, let's first try to understand how does the constraints or the marking of subformulas propagate within the parse tree. The forcing law of negation implies that the constraints or the markings switch their value from false to true and from true to false when they pass through a negation node. This can be seen in the top part of the slide. In case of a conjunction node, if the top node is true, both the daughter nodes will be true. Similarly, if both the daughter nodes are true, the parent conjunction node will be true. In case the conjunction node is false and one of the daughter node is true, the other daughter node has to be false and vice versa. In case one of the daughter node of a conjunction node is false, then this implies that the parent node, which is a conjunction, is marked as false. On the left is the parse tree of the transformed formula of the example we discussed. To start with, mark the topmost node as true, which is shown in the right part of the slide. Moreover, the timestamps are also shown within the directed acyclic graph. Since it is a conjunction node, both the daughter nodes will be true. Let's focus on the right side of the graph. Since there is negation, the marking constraint will switch from true to false. Similarly, marking on the timestamp 3 is false and on 4 it is true. Now we will apply the conjunction rule. Timestamp 5 will be true and timestamp 6 will be false. Note that there are some nodes whose markings can be calculated in two ways. Since there is no contradiction of marking of any node by calculating from any of the way, the formula that is given is hence satisfiable. Let us try to understand the complexity of linear SAT solver and why this type of SAT solver is called linear. So since the transformation of the given formula causes a linear blow up and marking is linear in the size of the graph, the runtime complexity of the SAT solver is linear and hence it is called linear SAT solver. You must be thinking about the limitation of the linear SAT solver Since 3-set problem is NP hard, so clearly there has to be some clauses which cannot be solved using linear SAT solver. Otherwise, we could have solved any SAT problem in linear time. We can note in the case when a conjunction node is false and none of the children node are marked, then there can be two cases possible. This condition was not mentioned in the linear SAT solver, and hence linear solver fails for all formulas in which the conjunction node is false and children node are not marked. And this type of formula is given in the above slide. Consider the formula shown in the above slide whose satisfiability needs to be checked. Let's try to solve this using a linear SAT solver that we studied in the previous slides. The directed acyclic graph for the above formula is shown in the next slide. We can observe that in this directed acyclic graph of the example, if we start from top by marking the topmost node as true and then applying the rules of negation as well as conjunction that we studied earlier and moving from top to bottom, then we can observe that on the leftmost arm of the graph, on the sixth timestamp, there is a conjunction node which is marked false, but none of its children are marked. Similarly, on timestamp 4 and timestamp 5, there are conjunction nodes which are marked false, but none of their children are marked false. So in this case, the algorithm gets stuck and we need to get away out of it. The cubic SAT solver provides a way out of this stuck condition. This is precisely the major difference between the two SAT solvers. The solution is to choose a test node n and then apply these two steps. Step 1 is to determine which temporary marks are forced by adding to true mark only to node n, and step 2 is to determine which temporary marks are forced by adding the false mark only to the node n. If both runs find contradictory constraints, then the algorithm stops and reports that phi is unsatisfiable. Otherwise, all nodes that received the same mark in both of these runs receive that very mark as a permanent mark. So in the previous problem, let us consider the directed acyclic graph. Let us mark the test node A as true. This node is pointed by an arrow on the left. Now we can observe that this marking produces a contradiction on the node which is pointed by arrow on the right. Hence, this marking of true on the test node is not true. So let's see what happens if we mark this node as false. Now, let us mark the test node taken in the previous case as false. Now, we again observe that this marking of false produces a contradiction on the conjunction node, which is pointed by an arrow on the right hand side. Now, since the test node cannot be marked true or false, since both of these markings produces a contradiction at some node, so this implies that the given formula is unsatisfiable. Let us have a brief recap. So in this presentation, we first learned about horn clauses, and then we moved to horn satisfiability. After that, we used the concept of markings to learn about linear set solvers, and then we found a limitation of linear set solvers which was solved by cubic set solvers, and hence we moved to cubic set solvers. So this was the flow of the presentation.